Hello, and welcome to the System Basis Chips overview. Our agenda covers what are System Basis Chips, or SBCs, why integrate with an SBC, the categories of SBCs including general purpose, mid-level, and advanced feature, with some final notes on industrial and automotive applications that can benefit from SBCs. So, what is an SBC and why is it needed? With increasing IC complexity and density in many systems, solutions with higher levels of integration become more attractive. Integrated solutions decrease the number of ICs needed in a system and help simplify the control system. Most modern automotive and industrial systems that require the use of wired communications, power regulation, fault detection, and bus diagnostics also need a robust control system to meet the demands of the current market. As you can see, we have an example showing that the SBC could be used to replace a discrete voltage regulator, high-side switches, and transceivers, simplifying overall design. Integrated solutions reduce the number of ICs required to support every design function. An integrated SBC solution can simplify and scale an overall design or application. The basic concept behind an SBC is an integrated solution that combines wired communication, power regulation, and protection feature functionality, using a straightforward control system that is integrated into one single package. We have generally seen SBCs classified in three groups: general purpose, mid-level, and advanced feature, based on the level of features integrated. Looking at our SBC wheel, we can break down each category of functionality that may be included in the SBC. At the top, we have protocol-specific transceivers, which generally are going to be either CAN, LIN, or both CAN and LIN transceivers. Moving clockwise, we see supervision, which includes fault monitoring, such as voltage monitoring and watchdog timers. Next, we can see the possibility of including high-side switches that can be used to conduct current to loads. These can be used in place of discrete load switches for lower current applications. At the bottom of the wheel, it shows that some SBCs will also include an integrated protocol controller, allowing more flexibility in the subsystem's main controller. Some SBCs will also include specialized logic outputs that can control other discrete transceivers, allowing for channel expansion to be facilitated by the SBC itself. Finally, all SBCs will have some voltage regulation abilities, either in the form of LDOs or switching converters, such as a buck. Now, let's focus on types of SBCs. There are three categories: general purpose, mid-range, and advanced feature. You can see some high-level differences in this diagram. General purpose. These are base-level SBCs. They contain a transceiver for wired communication, voltage regulators, and some basic protection features unified by a simple control system. General-purpose devices can replace any CAN or LIN transceiver, and potentially any voltage regulation needed. These devices require a protocol-specific companion controller, or MCU, to communicate via 4-wire SPI. TI families that are considered general-purpose are TCAN 11.6 for CAN communication and the TLIN 1028 for LIN communication. Mid-range SBCs. These SBCs expand on general-purpose SBCs with, at minimum, the addition of a high-side switch module, as well as the potential for additional transceivers and additional buck converters, or LDOs. Similar to the general-purpose SBCs, these must include a protocol-specific controller, or MCU, to communicate via 4-wire SPI. TI families to highlight here are the TCAN 24 for CAN, TLIN 14 for LIN, and TCAN 28 for CAN and LIN. Advanced feature SBCs. These SBC devices have one main distinction from mid-range devices. The advanced feature devices integrate a protocol-specific controller, as well as being able to communicate to other controllers via a SPI bus and various GPIOs. The integration of the protocol controller can increase the MCU's options for the designer to choose any MCU, as the MCU no longer needs to have a protocol-specific controller. These devices also tend to be feature-rich beyond the integration of the protocol controller. So, with the basic understanding of TI's SBC offerings and the general market applications, how can this aid a design engineer? To help illustrate the large range of potential applications, several different use cases will be discussed. General applications with general-purpose SBCs, 2 automotive applications with mid-range SBCs, and an industrial application using advanced feature SBCs. All SBCs combine wired bus communication with basic power management in a single package. Yet to determine if an application will benefit from the integration of an SBC, and to pre-select the SBC, here are the top 3 questions that any designer should consider when looking at their system. Does the system need bus communication and power conversion from battery voltage? Can the power tree be simplified by general-purpose SBC, i.e., what voltage does the controller require, and does the controller have 5-volt tolerant inputs? What standard is used for communication? Is it CAN SIC, also known as CAN SIC, or is it LIN? The answer to question 1 should always be yes. All SBCs include an LDO to take battery voltage directly and step it down for powering the internal CAN bus and other external peripherals. The SBCs have a wide input voltage range, and they can power other components with a voltage output of either 3.3 volts or 5 volts. The second question is always going to be a bit trickier to assess. A good measuring stick would be to look at the controller supply voltage. CAN devices are generally going to operate at 5-volt supplies, while many MCUs are operating at 3.3-volt supplies. The third question is going to depend on the use case. Now let's look at some specific applications that would benefit from general-purpose SBCs. A good example of a system where SBCs may be utilized is an LED headlight control. The original reference has a separate voltage regulator, watchdog timer, voltage supervisors, and transceiver interface. Devices like TCAN1167 integrate the transceiver interface, voltage regulators, a watchdog, and has some basic voltage supervision that can replace discrete protection devices. Another general-purpose SBC to highlight is the TLIN1028. Devices like the TLIN1028 don't require a separate power supply, can work directly off of a 12-volt battery, and can be used as an external power supply with up to 125 milliamps of output current. While this is applicable to multiple applications, an interesting industrial application is in powered surgical tools for medical interventions. Looking at the original design, specifically in the wired interface block, we can see traditionally it is handled by RS-485. However, LIN devices can also fill this purpose, as these systems don't have as long of cabling that is expected in RS-485. LIN also has a more defined standard, whereas RS-485 is only a physical layer standard. When using a device like the TLIN1028, we don't need a specific power converter and can power directly off of battery, as well as powering other peripheral circuits. Finally, SPI communication and SBC configuration can be facilitated by the subsystem's MCU. Moving on to mid-range SBCs. These can fit into multiple applications, but some interesting ones to focus on are automotive body control modules and phone-as-a-key applications. An automotive body control module is a generic term for an ECU that controls body electronics within a vehicle. This includes, but not limited to, windows, mirrors, HVAC, locks, etc. via communication on a CAN or LIN bus. Using a device from the TCAN28 family, a design engineer can reduce the BOM count and board size by targeting the discrete voltage regulators, watchdog timers, voltage monitors, transceivers, and high-side switches to replace them with one single SBC. This can reduce the amount of choices that a design engineer would have to make during part selection, and the design process can be focused on one device instead of multiple. Another interesting application is phone as a key. This application allows a user to unlock their vehicle with their phone through a Bluetooth connection. The TCAN24 line is specifically a great device for these types of applications due to the wake and ID pins that can be used to indicate what portion of the car the SBC resides in. This helps facilitate a smooth transition between different BLE connected nodes in the vehicle. Since each BLE device will be advertising, the phone may not connect to the BLE node best for unlocking the vehicle. However, each node, when connected with a TCAN24 device, can quickly determine the ID pin configuration to help triangulate the best node to unlock the car. This creates a smooth transition that is unknown to the user while increasing the overall user experience. Not only is there a technical benefit, but a practical one as well. Since the wake and ID pins can be connected to battery, ground, or left floating, multiple ECUs with the same design can be used in a phone as a key system. The wake and ID pins can be pulled out of the harness, allowing the same design to be configured with different physical IDs at the assembly level instead of having to design multiple ECUs. Finally, advanced feature SBCs integrate protocol-specific controllers into the IC itself. These parts could be applied to the previously discussed applications, with the added benefit of being able to replace the existing controller. These types of devices can be used in industrial applications. A good application example is an elevator control system, where there are primarily two flavors of communication in these systems, RS-485 or industrial CAN. While RS-485 is very popular for this kind of application due to its simplicity, it lacks definition beyond the physical layer and supports protocols that have defined host nodes, which in elevator control systems isn't usually the case. This leaves a lot of room for the designer to decide how they're going to implement a message-based protocol on the RS-485 bus. This can be challenging and lacks standardization. This isn't an issue for CAN in industrial applications because the standard defines arbitration and collision mitigation that gives designers a well-defined set of rules to follow, making the entire design process smoother. The TCAN4550, TI's flagship advanced SBC, fits into this application by acting as the SPI communication transceiver and CAN controller for every elevator panel, as well as monitoring for safety critical sensors along the elevator cart, shaft, and cabling. Since every panel requires communication, power, and a controller, the TCAN4550 greatly simplifies the design by filling the need of all three functions. Thank you for watching today's video giving an overview of system basis chips, generally referred to as SBCs. For the latest information on TI's SBC offerings, please visit ti.com/SBC. And for questions, please reach out to us on e2e.ti.com.